Hi, I'm Maya. This is a talk about a paper I co-wrote with Tomareza and Michal Feldman, and it's called Contract Design for Sequential Actions. Contract design is one of the pillars of macroeconomic theory. And in 2016,
Can you speak up a little bit?
Oh, sure. I'll try. Please remind me if my volume lowers again. And in 2016, Holmster and Hart have actually received a Nobel Prize for their contributions to it. And central to this contract design field is the principal agent model. So we're going to start by seeing a real life example of it. Okay, so this is Klarna, they're a bank. They make money by issuing loans. So they get many applications, they need to decide which loans they want to issue. And they want to issue as many loans as possible, as long as default rates, that is how many loans don't pay back in full, remain low. So for this purpose, it would be useful for Klarna to have some sort of measure, maybe a score, for the probability that a given borrower, a given applicant, will not return the loan. So for this, they engage the help of a company called Pagaya, which I used to work at. Pagaya is a company that trains machine learning models exactly for this purpose. Pagaya gets risk scores for loan applicants. So Pagaya has a choice to make in this interaction. They need to choose which model to train. We're going to call this the blue model, the green model, and the orange model. So just to an overview, Klarna has a data set, they give it to Pagaya. Pagaya trains a model, so Klarna knows which models Pagaya may train, but doesn't necessarily know which one they chose. And then Pagaya gives back risk scores for Klarna's applicants. So defining features. The trained model's performance is stochastic. This is not in the sense that once the model is trained, the performance is stochastic, but rather in the sense that before Pagaya exerts effort and incurs the cost of training a model, we don't know how well it's going to perform. We may have some expectation. We may know how well these models usually perform, but we don't know before we train it. Secondly, different models could have different costs or expected performance. So maybe the blue model is more expensive to train than the green model, and maybe we're also expected to perform better. Finally, and this is very crucial, is that Klarna doesn't know which model Pagaya chose. Klarna only sees the scores that Pagaya gives it. So Klarna knows how well the model performs. Klarna knows the accuracy, but Klarna doesn't know the model that is actually working. Okay. So as I said, this was an example of, so our question is going to be, how should Klarna pay Pagaya in order to make the most profit? So let's go to the mathematical principal agent model, which this was an example of. This is the classical principal agent model. So for those in the audience who are already familiar with it, I will show our extension in a few slides. The principal agent model is a two-player game between a principal and an agent. In our example, Klarna was the principal and Pagaya was the agent. And how the game unfolds is that Pagaya chooses one of n possible actions. Call that action I. This leads to two things. First, Pagaya incurs the cost of taking this action. Taking actions is costly. Call that cost CI. And secondly, is that some outcome is realized as a result of that. So we have n possible outcomes, and outcome J is realized according to a known distribution associated with action I. For outcome J, the principal gets some reward, call that RJ, and the expected reward when the agent takes action I is going to be just this capital RI. Now, as stated so far, the agent has no incentive to act. Taking actions is costly and reaps no benefits. So in order to incentivize the agent to act, the principal defines a contract, which is some m-dimensional vector of non-negative numbers. And essentially what it is that the principal is committing to the agent for outcome J. If I get outcome J, I'm going to give you TJ in payment. This is the reason that the contract looks like this is that the principal does not know which action the agent chose. So in an ideal world where the principal does know, the principal would just pay the agent for taking the best action. But the only thing that the principal knows is the outcome. So they can only condition the payment on which outcome was realized. Okay, so we have this contract T, which the principal defined. And now the expected payment that goes from the principal to the agent is just going to be this capital T. And we have and now we can get the principal's and agent's expected utilities. The principal's expected utility is just the expected reward minus the expected payment. And the agent's expected utility is the expected payment that they get from the principal minus the cost of the action that they take. And our objective is going to be to maximize the expected utility of the principal. So the principal knows the setting parameters. So they know the costs of each action, they know the rewards for the outcomes, they know the distributions of outcomes associated with the actions. And the principal assumes that the agent always takes the action that maximizes their own expected utility. And now, knowing all of these things, the principal needs to figure out what contract will maximize my expected utility. And in this basic model, this is possible in polynomial time. But as we see more complex settings, sometimes we have to resort to approximating the optimal utility. Okay, I want to say one more word about the contracts. So the most general form of a contract is what we've seen, this n-dimensional vector. So here we're just specifying for each outcome. So conditioning on all of the knowledge that the principal has, we're specifying a payment. This may be complex. It may have some undesirable properties such as not being monotone. So there has been some focus on linear contracts, which are a type of simple contracts and are essentially defined by some parameter between 0 and 1, alpha. And what they are is, in a word or two words, profit sharing. The principal is committing to the agent, I'm going to share alpha of my reward with you. So TJ equals alpha times RJ. Linear contracts are widely used in the real world. You can think of commissions, and also widely studied in literature. And in our paper, we're going to see results for both general contracts and for linear contracts. Okay, so that was the basic principal agent model. What do we do in our paper? In our paper, we simply ask the question, what if the agent has multiple attempts? So let's go back to our example with Pagaya and the models that they can choose to train. It might be unreasonable to assume that Pagaya is only choosing to train one model. So maybe at first they train the green model, they incur the cost of training this model, and then they see that it has a 90% accuracy. That's pretty good, but maybe now Pagaya is thinking to themselves, wait, maybe the orange model can do better. So now maybe Pagaya will also incur the cost of training the orange model, and they will see that it has an 80% accuracy. Maybe at this point, they don't think it's worth it to try and train the blue model as well. So they just go with the green model that gets a 90% accuracy. And that's the outcome that Klarna as the principal sees. So this is the model. Yes.
How do you view these 80% and 90% interacting? Is 90%, kind of dominating 80%, or if you combine them, you could get even more somehow?
We assume that the agent only goes with one outcome. So here 90% is the outcome, and you can only go with one outcome.
Thank you.
Okay, so this 90% accuracy of the score is what the principal Klarna sees. And essentially what we've taken here, we've taken the principal agent model, the basic version of it, and we've had the agent's problem be a little bit different. So what are our results in this new, yes?
Also, sorry to clarify, is the cost, like, once the agent trains both models, that cost is like summed over both, like that's a sunk cost?
Yes, the cost is additive, exactly. That's exactly right. Okay, any more questions about the model? Cool, okay. So what are our results? When the actions are independent, so what we mean by that is that the action's outcomes are independent. The blue model's performance is independent of that of the green models. When the actions are independent, we have a polynomial time algorithm for computing the optimal linear contract. So the optimal linear contract is the best parameter alpha between 0 and 1 that maximizes the principal's utility, and we can compute this in polynomial time in our sequential setting. We also have a polynomial time algorithm for the optimal arbitrary contract. So a vector, an m-dimensional vector, this holds when m is constant. So when the outcome space isn't arbitrarily large, we can also compute the optimal arbitrary contract in polynomial time. When the actions are correlated, so by that we mean maybe the blue model, if the blue model performs well, we also expect the green model to perform well. When the actions are correlated, the optimal contract is NP hard to approximate within any constant. And also the optimal linear contract is NP hard to approximate within any contract. So we cannot hope for any good approximation of either the optimal general contract or the optimal linear contract. Let's talk for a second about the Pandora's box problem, which was introduced by Weizmann in '79. The Pandora's box problem is very closely related to the agent's problem in our setting. So the agent's problem is what we call choosing the best response, the best strategy once a contract has been defined by the principal. So in the Pandora's box problem, we have n boxes. Here we have n equals 5. And inside each of these is a prize from some known distribution. But the boxes are locked behind locks that it costs something to open. We're trying to get as high a price as possible, but it costs something to search for that high price. So how would that look? How does the search commence? Maybe at first we search the green box. So we open it, we incur the cost of 5 to open it, and we see that inside it, the realized price is 10. Cool. Maybe now we're hoping for better, so we're going to also open the gray box. We incur the cost of that as well, which is 8. And we see that inside it is a price of 20. That's even better. Maybe we think we can do even better than this. So maybe now we also open the blue box. We incur that cost as well. We see that the price inside is 12. And maybe now we think we're not going to get better. We might as well just go home. We take home the best price that we've seen so far, which is 20. And our utility in this specific instance is 20 minus 5 minus 8 minus 3, which is 4. And the question in the Pandora's box problem is how can we have a strategy that maximizes our expected utility? And Weizmann showed that when the boxes are independent, there is a very elegant and simple solution to this problem. At this point, I'm going to remind you that I started by saying that this is very close to the agent's problem. So if we think of each of the agent's possible actions as boxes, the cost of opening a box is just the cost of taking that action. And the price inside the box is just how much the principal is willing to pay according to the contract that they defined for that specific action's outcome. And so really, we get that maximizing the agent's expected utility is equivalent to solving an instance of the Pandora's box problem. And this helps us for our positive results. Yes?
So in your contract model, wasn't the game repetitive?
The contract is only defined once, but the agent has a dynamic aspect to their strategy. Does that answer your question? Okay, so now that we have this very elegant solution, thanks to Weizmann, to the agent's problem, I'm only going to give a very high level understanding here, but for positive results, what we do is we use, we try and gain insight into how this agent solution changes as the contract changes. And by gaining these insights, we can try and start to understand how the optimal contract looks like. So this leads me to the following question. What have we done? We've taken the basic principal agent model and we've changed the agent's problem. We've had the agent solve a different game. What does a good agent's problem look like? First, it needs to be relevant to the real world. Here we were motivated by a very simple question. What if the agent has multiple attempts? And that gave us the Pandora's box problem. But maybe there are other well-known computer science problems that are also good agents question that could also be relevant to the real world. Another thing that we want the agent's problem to satisfy is that we can have insight into how it changes with a contract, because otherwise there's really no hope for designing an optimal contract if we don't know how the agent responds to it. So I would like to leave you with a question of, could more classical computer science problems be good agents problems? I think that's interesting to consider if they could be relevant to the real world, like we saw that the Pandora's box is, and also if we could have insight into how a solution to them changes with a contract. So let's summarize. We've seen the sequential action contract model, which essentially asks, what if the agent now has multiple attempts at taking actions? And we've also seen the Pandora's box problem and that it is very closely related to the agent's problem in our sequential model. Under independent action in the sequential action contracts model, we have polynomial time algorithms for both the optimal linear contract and the optimal general contract when M, the size of the outcome space, is constant. And under correlated actions, it is NP hard to get any approximation, both of the optimal general contract and of the optimal linear contract. So what are some open questions? The computational complexity of the optimal arbitrary contract when M isn't constant is open. We don't know if it is possible, if it is hard, can it be approximated? I think that's interesting. Secondly, we've seen that when the actions may be dependent, it is NP hard, but maybe we can enforce some sort of structure of dependence that both makes sense and allows us to get some positive results in this model. And finally, as I've said, there might be other agents problems that are interesting to consider within the setting of contract design. That's it. Thanks so much.
Anyone have any questions?
Oh, so when you say correlated actions, do you mean like the panel responses are correlated?
Yes.
The words are correlated.
Precisely, yes.
Okay, and have you considered like involving some of the correlated panel response results? And or say, for example, like update the posterior distribution. Use the posterior distribution as the agent distribution, blah, 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 something like that.
So there is, if I understand the question, there is a model of the correlated Pandora's box problem. But similarly to how for a contracting problem, it is NP hard to get an approximation. Also for the correlated Pandora's box problem, it is NP hard to get an approximation, even in very simple settings.
Actually, as far as I know some approximation.
So maybe you're familiar with an approximation for the minimization variant of the Pandora's box problem, where instead of trying to maximize the expected reward minus the sum of the cost,
Yes,
we're trying to minimize. Yes, I think the motivation for considering the minimization variant is that the maximization variant is hard to approximate. That's my understanding.
Yeah, got it.
Do you know anything about, I mean, you have a polynomial time algorithm, which is beautiful. Do you know anything about the structure of the contract, what it might look like, what it might not look like? The optimal one?
Unfortunately, no. The way that our approach for computing the optimal contract is the very common approach of finding the optimal contract to incentivize some best response of the agent. And we showed that there's a polynomial number of best responses and it is possible to find any so we do not have some insight into how the contract looks.
Okay, thank you.